In high school, he took an AP stats class, and he complained that none of the methods made sense since they're all based on the arbitrary assumption that every relationship was a straight line. We all know about the best linear estimator, right? Best unbiased linear estimator. So his teacher told him statistics was not the subject for him. And over a decade later, he has a degree in statistics, and his job is literally to convince people stop using methods that draw straight lines. Please welcome George.
Right, hey everybody, it's great to be here. Today I'm going to be talking about Bayesian boosting, or how I learned to stop worrying and love uncertainty. So I want to begin by offering everybody a choice. We have some outcome of interest. You could imagine any outcome you'd like, just with the constraint that we want it to be higher. We want to maximize this outcome. And fortunately for us, we have a statistical model that's going to help us make a choice. And for option A, our model is going to tell us that we're expecting a value of 9. And for option B, our model is going to tell us that we're expecting a value of 9. And given this information, we really have no reason to prefer one choice over the other. Now, the only thing is, I've left out some information from our model. And that is, option A, according to our model, has a 95% chance of being between -3 and 11. Option B is predicted to be between 8 and 10. Now, this may make us think a little bit differently about which one we prefer. And so I'm going to use some hypothetical data. We could imagine any continuous outcome. If this was you could imagine it being a study of subjective well-being, and Z is a binary variable. It could be whether or not you're participating in a meditation program or an exercise regimen. And X could be the number of hours you're working every week. Y could be some variable like income. X is current earnings. Y would be future earnings. Z is whether or not you're enrolled in some type of jobs training program, or if you're not. Now, if we wanted to model this data, we could start with just fitting a linear regression, but it looks pretty nonlinear, so that's probably not a great start. There's also not a ton of observations, so methods like deep learning probably wouldn't fare particularly well. And so where does this leave us? Well, a natural approach would be using some type of tree-based method to model this. And we're going to build up some intuition, ultimately getting to Bayesian boosting, which is a Bayesian version of boosted regression trees. But before we get there, we're going to talk about tree methods in general. And so the idea of a regression tree, which is at the center of all of these types of tree-based methods, is if we could only make one cut in our data, what's that cut going to be? And then after making that cut, we kind of go in those two groups. What's the next best cut? And best is defined as where are we dividing up our data to get the best predictions. So this is a regression tree fit to our data. And if we kind of follow down, we have 199 people in our sample. So if you have a Z value of 0, it turns out Z is kind of the best cut first. You're over here. And then within Z values of 0, if you have an X value less than 12, you fall down to here. And the bottom of the tree, it's called a leaf, is just the prediction. So for everybody in this kind of cluster of data, we'd predict a score of 78. Now, if you had a Z value of 1, we would be over here. And then if you, let's say, a particular individual or a group of individuals with X values above 44 would fall over here. And then splitting on X again, we end up in a leaf down here. So for those folks with Z of 1, X over 44, and then Y over 52, they would have a prediction of 118. And so this is a way of kind of splitting up our data without making any pesky linear assumptions. So is our job done? Why not just use a regression tree? The problem is, where do we stop? We could just keep splitting and splitting and splitting and splitting until we just have a prediction for each person in our data set, and it's a perfect prediction. Now, that may seem very well and good, but most of the time we're not just interested about our sample, but making generalizations to broader populations. And if we use this model on unseen data, those predictions would be grossly overfit. So usually you rely on some type of cross-validation to kind of trim the tree and keep it a little bit smaller. There's a few different ways to do it. Sometimes you encode hard rules, like say, When we get to any of these splits, if there's less than 20 people in there, we're just going to stop. The tree can't get any deeper. Some people use explicit forms of cross-validation on out-of-sample tests. Here, I use some version of cross-validation. And if we look at how this fares on our test set, we have an RSME around 2. We can see we're kind of non-linearly modeling the data, and it's just making these kind of crude means within splits. If we look at how we perform on some unseen data, our error goes up a little bit, but it's not grossly overfit. Our predictions are still pretty well. But there may be a way that we can squeeze out some more predictive power. By instead of relying on one large regression tree, what if we harness the power of many small regression trees? And this is the intuition of what's called gradient-boosted regression trees. Instead of using one tree to fit our data, make predictions, we're going to force trees to be really, really small. And then we're actually going to use some parameters, usually they're called learning rate or shrinkage, to make those predictions even smaller. These learning rates are always less than 1. It's a tunable parameter. You tune it by cross-validation. And if you multiply a number by something less than 1, it's going to get smaller. So we have a little prediction from a little tree, and we're going to squeeze it even smaller. And we're going to do this a lot of times. Hundreds of trees, 100 trees, 150 trees. And we're going to sum up all of the values from this tree. Now, some people here may be familiar with random forest. We're not going to talk about that today. Just know that random forest is doing something very different. It's averaging over trees. This is a literal sum. And so each tree is contributing a tiny bit. In the case of gradient-boosted trees, all of the contributions is kind of dependent on the prior tree. And we tune a few parameters, like how many trees, how deep can the trees be? You have to set a max depth. Should we let it go down to 3? Should we cap it at 2? Should we let it go down to 6? That's a pretty deep tree. And all of these things have implications for whether or not we're overfitting our data. Now, this may still be a little bit confusing, so I'm going to walk through the process of what actually happens with gradient-boosted trees. So without any other information, the best prediction we have is just the overall average. So we start with this. This is the overall average. We're going to see how each of our points compare to the average, and we're going to save that. It's called the residual. And then we're going to fit a tiny regression tree on that residual. Tiny defined by the values of the hyperparameters we used. How deep can it be? And the shrinkage parameter. And so we're going to fit this. We're going to multiply the fits by the shrinkage parameter and add it. So this is our first tree. And as you can see, it's just a little prediction. It's not going to fare well on our overall data set. We're going to compare how the residuals are to this tree, multiply it by the shrinkage parameter, and then sum up tree 1 and 2. And that gets us here. We're going to see how the residuals compare to this fit another tree on those residuals, multiply by the learning rate, aka shrinkage parameter, and we get this. And we're just going to keep repeating, and slowly, our model is going to get more and more and more flexible. Jumping ahead to the 50th tree, to the 10th tree, we get something like this. And then if we jump ahead to the 50th tree, we see it's continuing to grow and grow and grow, just very, very slowly. And the slow growth is what prevents us from overfitting. And if we see how this fares on our training set, we've picked up much better predictions. Our model's much more flexible now. It's really hugging the points tightly. But this is the training data set. And the question is this too good to be true? If we saw some unseen data, maybe things are a little bit different. So we have a little bit more error, but our regularization is still performing pretty well. And this is because I cross-validated this GBM model, this gradient-boosted model, specifically running many models on subsets of the training set to kind of optimize these parameters. And it takes a lot of time, and there's many ways to do it. And there's a lot of unknowns. How long do we cross-validate? What options do we use? These are all things that are kind of left up to the user. It's very time-intensive, very computationally intensive. But our prediction is still much better than our single regression tree. So we're making progress. So even though gradient-boosted trees has given us better predictions, it's not answering that uncertainty part of the problem. If I gave you a prediction somewhere in this tree, I don't know how credible that prediction is. How much should I believe it? How much does our model really believe that prediction? And to answer these questions about our model's uncertainty, we need to move into a Bayesian framework. There are other ways to talk about uncertainty, but a natural way is a Bayesian inferential framework in which we're going to keep the non-parametric machine learning approach and combine the inference abilities of Bayesian inference. This is the formal model for the Bayesian version of regression trees. It's called Bayesian Additive Regression Trees. We don't need to get too into the math. The only details to know is this just means it's a sum of many, many small trees. There's some error term learned from the data. We're going to assume it's independent. And just like with gradient boosted trees, we're going to sum all of them up. Now, the difference here, G on all of those trees, we're no longer setting things like a learning rate. We've thrown that away in the Bayesian framework now. We're going to rely on Bayesian priors to shrink all of these trees. So in this equation, G is going to be the new equivalent of that 0.1, that learning rate, that shrinkage thing. But we're not explicitly setting it. We're not going to cross-validate it. It's just going to be we're going to talk about these beliefs in a little bit. M is just M is the means, T is the trees. So within each tree, we have means for people. Just like the first regression tree, we just have a lot of really small ones. And we're going to draw from a posterior distribution with a Gibbs sampler. If you don't know what that is, it's not important. This is still a little confusing how this works. So we're not cross-validating anymore. And in the Bayesian framework, we're not even really fitting trees the same way anymore. What's going to happen is trees are going to be proposed. We have a certain amount of rules that trees could be. Maybe we want to grow a tree deeper. Maybe we want to make a tree smaller. Maybe we want to kind of change things around in the tree. What if we just kind of experimented by flipping those split rules? These are all different types of proposals we could make. And we're going to propose a given tree, and which type of rule we use, it's just going to be kind of randomly picked. And whether or not we accept that proposal or reject it is going to be a decision made that favors improving the fit. It's not a hard rule. We're not going to pick anything that automatically improves it. There's still a little bit of randomness in there, but we're going to favor stuff that slowly improves the fit. Now, I talked about that G parameter, how we're kind of throwing away the idea of a learning rate. So how do we do that? Well, we have some beliefs about how trees should look. And we're going to use probability distributions to add those beliefs into our statistical model. So I'd like to talk about what are our actual beliefs about our trees. Well, we believe we should be skeptical about predictions that are really far from the average. If our model was giving us a total ton of extreme things, really, really outliers, it's kind of a sign of overfitting. So we should be a little bit worried about that. And if we see a lot of extreme predictions, maybe we want to kind of pull them into the center a little bit. We also know that trees should be small. We know this from GBM, we know this from regression trees. If you let them grow too deep, we really start ramping up the risk of overfitting. And we also believe that our model should be able to outperform linear regression. This is usually used in cases where we believe the data is not linear. In this example, in two-dimensional space, we can explicitly see that it's not. In higher dimensional space, it's very rare that data is actually linear. So in some ways, this is even the best situation. And we already know that assumption is failing. So we believe our non-parametric models should do a little bit better than that. And so we incorporate those beliefs into explicit priors. We have a prior on the means, which is just those leaves of the regression tree. It's our predictions. We have a prior on the trees. We have a prior on the error term, which is just our residual. And these priors are going to give us strong predictive performance without the need to rely on cross-validation. And all of the results I'm going to show you with BART have been done with no cross-validation at all. I just used the default, put in the data and fit, and this is what it spat out. Now, we can talk a little bit more about the priors. I'm not going to get into it too much. You can read more about this outside if you're really interested in it, or you can talk to me after. But the gist of it is we're going to scale all of the data. So the mean 0, the mean is the average, and we can see extreme predictions, and if they're extreme, we're just going to pull it back in. We think that about 95% of our data should be a couple standard deviations away from the mean. That's the idea of the prior on mu. Prior on t, we're going to give probabilities that trees can be certain depths. So we know we probably need more than a depth 1, so we'll give that about 5%. Most of the time, we want to be in the depth of 2, depth of 3, so we've got a 55% chance of proposing a tree that is depth 2 and a 28% of depth 3. And then we've got depth 4 and 5. Now, this is not a hard cap on 5. If the data demands it during this kind of proposal process, remember, we're going to slowly favor fits that improve the overall fit. We're going to favor trees that improve the fit. So it's possible to have a depth of 17. In some of the initial work on this, they saw trees with a depth of 17, and they were counteracted by many, many trees of a depth 1. So it can happen if the data demands it. And all of this is just due to this kind of Metropolis-Hastings proposal rejection system. We have some prior on sigma. I'm not going to get into it too much. We calibrate it explicitly with a linear regression. So we fit it with a linear regression, and we usually pick kind of a default distribution saying it's distributed chi-squared, and we think our model is going to fall within this range compared to linear regression. And it's just kind of giving us a starting point to inform how much error to add to our predictions. So I've been talking about this hypothetical case, 200 people, 2 variables. What I say may be interesting, but may feel a little bit ungeneralizable. So this is some data from the initial paper about BART, Bayesian Additive Regression Trees, i.e. Bayesian boosting. And it shows that with default BART, without any cross-validation at all, it's performing better than other top-tier machine learning algorithms like boosting, neural networks, and random forests. And this is just straight out of the box with no cross-validation, whereas all of the other models have been cross-validated. And these results are from 42 data sets with 800 trained test splits. So this is a more generalizable type of sample. And then when we do cross-validate BART, which you can do, some of these priors you do have to set certain distributional assumptions about. You can tune the values of these distributions a little bit and further improve performance. But even if you don't, your predictions are still going to be really good. So how does all of this translate to our data? I'm going to speed up a little bit. This is just some examples. We're going to randomly fit the trees. This is an example of a tree that got accepted. Another tree gets proposed and accepted. This is an example of a tree slowly growing. This is an example of when we flip trees. A lot of random proposals are happening. We're just proposing new type of tree, and it's either going to get accepted or rejected. There's some cases where trees don't change. See, this is staying the same because our proposal is rejected, so we're going to stay the same. And we're just going to slowly build a forest of trees just on this probabilistic accept, reject, kind of trading back and forth. Sometimes our trees get really small. All of these things are possible within the framework I've outlined. And now applied to our own data, our train set's really amazing. Now, we may be looking at this and be like, there's no way this isn't overfit. And if you look at the test set, it's not particularly overfit. In fact, our test set error is lower than the training set for gradient boosted trees in this example. And this is without any cross-validation at all. Now, that last plot was even an oversimplification. These lines aren't the real predictions. Each prediction is a distribution. And so if we wanted to zoom in on an individual, we have a whole distribution quantifying how credible we think this prediction is. Because sure, our model thinks that a value of 105 is more likely than 102, but 102 is still likely. It's still possible. And we can quantify how likely our model thinks this is. And this is getting back to what I opened with, of knowing information about the uncertainty in our model can be a really important asset when we're trying to make decisions. Now, sometimes we end up making predictions in areas that we haven't seen before. So you could imagine we fit a model based on our training set, and then this red point shows up. And we want to make a prediction about him. Now, the issue is they're kind of in this group down here. This is a value of z0. But we don't know what happens to z0 folks over here. So all of our models are blind. And machine learning can't really fix this. But it will give a prediction. Here's our prediction from gradient boosted trees. Here's our prediction from a regression tree. And it's going to give it to you, and it's going to be very confident in that prediction. In fact, it's just going to give you the number, and you have to believe it. But what if we could actually quantify that we're really uncertain over here? And so as we extrapolate into areas of the space that we haven't seen before, BART is going to be honest that it really is not comfortable with the prediction. So here we're not even covering the real observation. But the distribution grows to the point where if you looked at the distribution, you would know we're extrapolating to areas we probably shouldn't be. And in multidimensional space, you wouldn't be able to see that there's no data here. But the uncertainty would still exist. So using BART-based methods allows us to recognize when we're kind of extrapolating into areas that we shouldn't, even if we can't directly see it. Now, most of my work, we're expanding this into causal inference. You could really think about causal inference as a prediction problem. We're not just interested in predicting individuals, we're interested in predicting what would have happened if we flipped somebody's value of z1 to z0. In other words, what's the causal effect of z on y? And these tools can be really useful. In the same way as we get a prediction for an individual, we can also get predictions in coherent, credible intervals that can be interpreted as probabilities about entire groupings of parameters. We can make statements about the relationship between z and y, given a certain set of causal assumptions is satisfied. If you're doing causal inference, you should read up on what those assumptions are. Here we're making a heavy, heavy assumption that we've measured all confounders. And we can automatically detect any heterogeneity in our treatment effect. Thanks so much. If you're interested in learning these methods, using these methods on your own, implemented in R in the dbarts package, BART causal inference, stand for BART for multi-level models, and thinkCausal if you want to use a point-and-click system and don't want to worry about any of the programming of this.